Hi everyone, this is Prof. K speaking, and today we're going to talk about writing and balancing chemical equations. And so to start, a bit of review. So far in this course, we've been talking about how we represent atoms and elements, what their electron configurations look like, how we start to do bonding between different atoms and start to form compounds that have particular shapes and properties. And now what we want to move into is how do we combine compounds or molecules with other compounds and elements to do interesting reactions? And how do we represent and describe those reactions so that we can understand them and share them with each other and know what we're talking about? So the learning objective of this video is to practice deriving chemical equations from narrative descriptions of chemical reactions. And so on this screen is an example of a chemical reaction, which instead of describing, I've drawn to start with so that we can talk a little bit about how we talk about reactions using different language so that we know what we're discussing. And so the first two sort of language tools that we use is that we talk about there being a reactant and a product side of the chemical reactions. The reactant side is the compounds or elements that are reacting to produce the products. So if you're ever uncertain which is which, just think about what is reacting in my system and what is being produced. And so if we look at this chemical equation on the left-hand side, our reactant side, we start with 1 carbon, 4 hydrogens, and 4 oxygens bound in the form of a methane and 2 O2 atoms. And then on our product side, we've rearranged those atoms to produce 1 CO2 and 2 waters, or H2Os. And so when we look at the number of atoms on each side, in our product, we still have 1 carbon, 4 hydrogens, and 4 oxygens. So we didn't get rid of any atoms. All we've done is rearrange the types of bonds they have to form new compounds. So this process of rearranging the bonds is a chemical reaction. And what we put into our system is our reactant, and what we get out is our product. So I just wrote on this slide, kind of in the notes, is the molecular formulas of these systems, which we've also been practicing naming. So we have methane and oxygen gas react to form carbon dioxide and water. So this is a narrative description of the pictured reaction that we can then convert into a molecular formula, or the molecular process that we have here. And you might notice looking at this slide that I don't just have 1 methane and 1 oxygen combining, and instead I have actually 2 oxygen gas molecules reacting with 1 methane to form my single carbon dioxide and my 2 waters. And these coefficients tell us how much of a particular molecule we need to do the chemistry we need to do. And so what this is telling us is that in order to represent this full equation, we have to identify our reactants using their molecular formulas, and then we have to provide the coefficient that tells us how much of each molecule we have in order to do the chemistry that we're interested in. And this representation of the reaction is helpful to us because it can then tell us the stoichiometric ratio of our different molecules in our system. And so what this tells us is that for every 1 mole of methane and 2 moles of oxygen that you react, you can form or produce 1 mole of CO2 and 2 moles of H2O. So we call these coefficients the stoichiometric coefficients, and it helps us understand the stoichiometric ratios between different products and reactants. So if I give you a problem where I say that I react 1 mole of methane with excess CO2 or excess oxygen, so as much oxygen as you want, and I ask you how much or how many moles of water can I produce? It tells you that you can produce 2 moles of water. So if we change the numbers here to me providing you with 3 moles of methane to start, then hopefully you can recognize that you're able to produce 6 moles of H2O. So there's this ratio that we can multiply our inputs by to get our outputs. And another way that we can sort of think about this is that if we look at figure 7.3 in the book and we count how many molecules exist in any given reaction system, we can react 3 CH4 molecules and 6 O2 molecules to produce 3 CO2 molecules and 6 H2O molecules. And what this tells us is that we have some reaction happening that's occurring at some multiple of the reaction that we wrote on the last slide. So if we reduced each of these values, at the reaction level, what's actually happening is going to be 1 methane is going to react with 2 oxygens, and out will come 1 CO2 and 2 waters. And this reaction can happen in this system 3 times because we have 3 times that number system. So we can have another methane react with 2 oxygens to produce another CO2 and 2 waters, and then we can repeat that to produce the sort of last reaction that happens, which is another methane and 2 waters react to form a CO2 and 2 water. Or sorry, on this side it's methane and 2 oxygens and CO2 and 2 waters. And so our reaction representation that we had on the prior slide, which was CH4 plus 2O2 forms CO2 plus 2H2O, tells us the minimum requirement we need to do this reaction and is a better representation of our system than using these 3s and 6s. So we always want to reduce the equation that we have to the minimum integer number of molecules that we can handle in this system. And the reason that we use integer numbers is something we're going to explore in this little practice problem. So I'd like you to consider that if a professor on a test asked you, what is ethane combustion going to be in terms of a balanced reaction? And so ethane combustion is ethane plus oxygen gas produces carbon dioxide and water. Your classmate proposed this expression on the test and is marked incorrect. And I want to give you a minute to think about why this notation is incorrect, and then we'll work through it as a problem. So take a second and think, why is this notation incorrect? And you can pause the video and try to work it out if you'd like. Okay, so hopefully you took some time to think about this. And when we look at this reaction, if you count the number of carbons and oxygens on each side, you can see that we actually do have a balanced number of atoms. So we have 2 carbons present on each side of this reaction. We have 6 hydrogens present on both sides and 7 oxygens present on one side. The problem that we face in this description of it is that if you have 7 halves here, then what you're saying is you have 3.5 O2s. And that manifests as this open sort of oxygen radical hanging around. And this doesn't reflect the chemistry that we're doing. So instead, if we multiply this reaction as we wrote it by 2 to write 2 ethane, 7 oxygen, 4 carbon dioxides, and 6 waters, Then we don't have any incomplete molecules. Our oxygen is actually O2 gas, and it can form the products that still have a balanced number of carbons, hydrogens, and oxygens. And so it's important that we don't use fractions in our expressions, because otherwise we're sort of inventing new chemistry. We're breaking up structures. This symbolism has a meaning, and it means that it's this molecule multiplied by that. And we don't want to multiply a molecule by a fraction, because that's not doing the chemistry that we're talking about. And so to practice how we would balance a reaction instead of the last problem where you're sort of seeing what might be wrong with one, I want you to consider the photosynthesis reaction. So if you'd like, you can pause the video again, try to work out the balanced reaction for this, and then I'll walk you through it. So hopefully you got the opportunity to work through this example, but now I'm going to try to balance it. And so the first thing I like to do when I start to solve this problem is I like to count how many of each atom we have on both the reactant and the product side. So we start with 1 carbon, 2 hydrogens. Oh, let me erase that real quick. 2 hydrogens, and we have 3 oxygens. And on our product side, we have 6 carbons, 12 oxygens, or 12 hydrogens and 8 oxygens total, because we have 6 here and 2 here. And so the first thing I noticed is that we need many more carbons in our reactants in order to produce glucose over here. And so the first thing I might attempt, and I'll do this in a different color so you can see the sort of iterative process I go through. And so if I put a 6 in front of CO2, then I get a new count for my system. So I now have 6 carbons, I still have 2 hydrogens, and now I have 13. Yes, 13 oxygens. And I didn't change anything on this side, so these numbers are the same. So 6, 12, and 8. So now when I look at the system, I notice that O2 is by itself, whereas hydrogen is bound to oxygen in water. And so the next thing I might try to do is try to balance the hydrogens. And so in order to get up to 12 hydrogens in glucose, I need to multiply my water by 6, which I'll do in another color. So if I multiply my water by 6, I still have 6 carbons. Now I have 12 hydrogens, and I have 18 oxygens. So 12 oxygens from CO2 and 6 from water. And on the other side of my expression, everything's still the same. So I have 6, 12, and 8. So now my carbon and my hydrogen are balanced, but my oxygens aren't. So I already have 8 oxygens, but I want to get up to 18. And so since there are 6 oxygens in glucose, I need 10 oxygens from O2, which means that I'd want to put a 6. That I need 12 oxygens in O2. So then this is my last change here, which I'll do in another color. Let's try. One second. Okay. And so if I have 6 oxygens to get up to 6 O2 gases, now I'll have 6, 12, 18, and 6, 12, 18. So now I've balanced the atoms here. I only have full molecules, and I can't divide this reaction by anything. So it seems like I've correctly balanced this chemical equation, which is good and helps us try to predict that if I want a plant to do photosynthesis, I need to give it at least 6 carbon dioxides and 6 waters, and it will produce for me 1 glucose and 6 oxygen molecules. And we can say this again in terms of moles. So 6 moles of CO2 plus 6 moles of water will produce 1 mole of glucose and 6 moles of oxygen. And so in addition to being able to use a balanced chemical reaction like this, there's also other information that we can include here to help us understand what's happening in our reaction system and what state it's in. So if we want to, we can describe the phase of the system. So CO2 is a gas when a plant ingests it to do photosynthesis. Water is a liquid. Oxygen that comes out is a gas. And this aqueous here is actually a little dependent on the field that you're in, but what it can mean is something in water. So aqueous. But another way that some biologists like to represent this is instead to say this is a solid, but the system is in water. So I just wanted to show you there's sort of different options here. And so S stands for solid. And so we can specify the phase or the state of the atoms in these systems. And in addition, if you need something extra to help you do your reaction, you can also include it above the arrow as an annotation to this. So hopefully, if you've sort of taken bio before, you know that in order to do photosynthesis, you need sunlight. So you can represent the need for light as H nu over your reaction, which is sort of a throwback to when we talked about doing absorbance and emission, that we need some sort of light into the system to drive it. If instead of light, the system needed heat, we would draw this little delta above the reaction. And so these are some common symbols you might see as we start to write reactions and try to describe what phase they're in or what state. And so now we have another practice problem that you can do. And so this is a narrative practice problem, which is that Professor McKenna would like you to predict and balance the chemical equation for reacting hydrochloric acid with potassium hydroxide. And then if we can figure it out, we'll try to include phases if possible. And so I'd pause the video and work on it by yourself, and then I'll explain how I would approach this. Okay, so we're told in this problem that we're reacting hydrochloric acid, which is my first reactant, with potassium hydroxide, which is my second reactant. So if I write the molecular formula for hydrochloric acid, I would write HCl, and then I would add it to potassium hydroxide. So potassium hydroxide, and then we're going to form something. And something that we've practiced in the course that we'll talk about in more detail is that oftentimes when you're trying to predict reactions, you'll sort of switch the sort of beginning pieces in the molecular formulas because these represent the more positive components. So this looks like H plus and Cl minus, and then we have K plus and OH minus. Here is sort of what the charges look like. So we'll try to switch them, which produces HOH and KCl, which we'd more commonly write as HCl plus KOH, produces H2O and potassium chloride. And so if we count the atoms we have on both sides of this expression here, we have 2 hydrogens, 1 chlorine, 1 potassium, and 1 oxygen. And on our product side, we still have 2 hydrogens, 1 chlorine, 1 potassium, and 1 oxygen. So this is the balanced chemical equation, which we've just derived. And we'll practice doing this more in class next period. So that's it for today, and go check out the next video.